Alrighty, in this last section, we're going to be working on problems where the range equation does not apply. And if you remember, the only time you can use the range equation is when the elevation at which the projectile is launched is the same elevation at which it lands. The problems that we're doing in this section, that will not be the case. The projectile is not going to land at the same elevation from which it's launched. So we have to use our other equations. The range equation won't work. So as we start working these problems, we need to review some of the same things that we've already talked about as far as principle. Remember, x and y components are independent of each other. In the x direction, in the x component, the velocity is constant and acceleration is 0. In the y component, acceleration is negative 9.8 meters per second squared. The velocity of the y component is 0 at the maximum height. We also have said that we have to calculate time from the y component because that's where the acceleration is. Once the projectile hits the ground, there's no motion either in the y direction or in the x direction anymore. So the horizontal and vertical distance, if we need any kind of time to determine that, that has to come from the y component because the object is not going to travel any further once it hits the ground. It can't travel any further horizontally anyway. Okay, so we're going to try to keep those things in mind. Now, in this video, I'm going to be working 3 specific problems. So I'm going to tell you a little bit about those problems before I start so that if you understood part of it, you can fast forward if you don't want to watch the whole thing. The first example I'm going to work is example 4.5 from your book, and that's the one where we're going to be calculating a horizontal displacement. Example 4.6, a very similar problem except we're going to be calculating an initial velocity. And the last problem I'm going to work is one where we actually have an initial launch angle. Both of these problems, the initial launch angle is 0. It's launched horizontally. It doesn't have an initial launch angle. So that initial launch angle is, I'm going to include that in the third problem that I work, and there's not one like that in your book. Okay, so we're going to start over here with example 4.5. If you don't want to watch this one, then kind of fast forward the video until you see me start working on this part of the board. If you don't want to watch either of those, just fast forward the video till you see me erase the whole thing, and then we'll start with a new problem there. So let's start with example 4.5. A cannon shoots horizontally, theta equals 0 off of a cliff. The cannon can shoot with an initial speed of 150 meters per second and is 100 meters above the ground. How far will the cannonball be from the cliff when it finally hits the ground? So the only thing I didn't put up here is that the initial velocity is 150 meters per second. And again, if they don't provide a picture for you in the problem, you need to draw one so that you can be sure that you can see exactly what's going on. So here's my cannonball being shot off of a cliff. It is 100 meters high. I'm trying to find this displacement. Theta equals 0 because it's being shot horizontally. Now, I want to point out to you that your author uses the sine and the cosine to calculate the components of the velocity in the x and the y direction. There's nothing wrong with doing that. You can certainly do it that way, but you can also save yourself a little bit of work because there is, I can't say there's no component in the y direction. There is a component in the y direction, but the y component of the velocity at launch is 0 because they told you that the velocity that the cannonball was being shot at 0 degrees. So we already know that in the y direction, the initial velocity in the y direction is 0 because it was being shot at 0 degrees. Okay? Therefore, that means that the initial velocity in the x direction, all of the velocity is in that direction, so the initial velocity in the x direction is 150 meters per second. So that little shortcut can save you a little bit of time when you're working some of these problems if they tell you that theta equals 0. You don't actually have to calculate it out. Okay, now, we were being asked for this displacement. in order to find displacement, I know that delta x equals v sub 0 t plus 1/2 at squared, right? That's the equation I'm going to have to use for this. I know the initial velocity. I don't have any acceleration in the horizontal direction, but the problem is I don't know the time. And so we had said before that the time is always determined from the y component. So I've got to look at the y component first in order to calculate the time. I'm actually going to use this same equation to calculate the time, because here I know the vertical displacement. So here I'm going to put y component up here just so you don't get confused. So in the y direction, I know that my displacement was a negative 100 meters. Why is it negative? Because this is where it started and all the displacement was in a downward direction, okay? So I know that the initial velocity in the y direction was 0. It started out at 0 degrees, and so I didn't have any velocity in that direction, or in that component. So then I'm going to have 1/2 times negative 9.8 meters per second squared times t squared. So then when I solve this equation for t, I'm going to end up with 4.5 seconds. Okay? So now that I know the time, now I can move to the x component and I can calculate the horizontal distance, because again, delta x equals v sub 0 t plus 1/2 at squared, while up here, this component, or this part of the equation dropped out because the initial velocity in that component was 0. Here in the x component, the acceleration is 0, so this piece drops out. So here, my delta x equals v sub 0 in the x direction is 150 meters per second. I calculated the time from here, which is 4.5 seconds. And so that is going to give me a delta x of 680 meters. Okay, so this is a classic example of a problem where I know initial velocity, I know a vertical distance, I'm trying to find a horizontal distance. The only way I can find the horizontal distance with the information that I have here is the fact that I'm going to have to know time in the air, and time in the air has to be determined from the y component. Okay, so now let's move to example 4.6, and here I have an archer who is shooting an arrow, and obviously if she shoots horizontal, again, theta equals 0 degrees, she knows that she's 50 feet away from this tree, and when she shoots horizontally, she finds that the arrow drops 4.12 feet. And the question we're asked this time is, what is the initial velocity? Okay, so what am I going to do this time? Well, for starters, I'm still going to need to know x and y components of that initial velocity, but I know that there is no y component, or that the y component of the initial velocity is going to be 0 because she's shot it horizontally. So again, if I look at the y component, that's where my time's going to come from, and I can't figure out what velocity is if I know distance and I don't know time. That's what the definition of velocity is. It's distance divided by time, or displacement divided by time. So I have to know the time. Again, if I need the time, I have to go to the y component to get it. So if I know delta x equals v sub 0 t plus 1/2 at squared, theta is 0. There is no velocity in the y direction. It's equal to 0, so this part drops out. So here, the delta x in the y direction is 4.12 feet. Notice it's in feet this time. It has dropped, so this needs to be negative. Then I have 1/2 times a negative 32 feet per second squared. Remember, my units have to match, so I have to use this acceleration due to gravity. And then I can solve for t squared. I'm going to have my negatives are going to drop out, and so when I end up solving for that, I'm going to end up with t equal to 0.51 seconds. Okay? Now I can use that very same equation to calculate the initial velocity in the x direction, because again, all the velocity, the initial velocity was all in the horizontal direction this time because theta was equal to 0. So if I use this same equation, delta x equals v sub 0 t plus 1/2 at squared, no acceleration in the x component, so this piece drops out. The horizontal component of this is 50 feet. Initial velocity is what I'm trying to find. The time is 0.51 seconds, and so therefore when I solve for the initial velocity and I divide that out, I'm going to take 50 divided by 0.51, and that will give me 98 feet per second. I did drop a significant figure there. Sorry about that. That should have been 50.0. I forgot to put it in there when I had it, so I did end up with 2 significant figures in my final answer. Okay, so again, this similar type of problem, I was looking for something different. I was looking for initial velocity this time, but I still had to go to that y component to figure out what my time was going to be. Okay, so those are the 2 examples in the book. Now we're going to move to an example that has velocity that starts out at an angle, and so that one is going to be worked. The principles are still the same, but you have to be a little bit more careful with your velocity because you're actually going to have to calculate those initial velocities. So in this problem, let's say that we're sitting on a cliff, because all the physics problems start on a cliff, right? And so we're up here on top of this cliff, and we're going to throw a rock off of it, because what more fun is there than throwing rocks off of cliffs, right? So we're going to throw a rock off of a cliff. Here's our rock. And we are going to throw it at a theta of 30 degrees. And let's say that we're going to throw it with an initial velocity of 8.5 meters per second. Okay? I know that this cliff is 100 meters high. And what I want to know is, once this thing falls, what is my horizontal displacement going to be? Where is it going to hit the ground? Okay, so that's what I'm asking for. How far from the edge of the cliff is it going to land? That's all the information I know, but thankfully that's all the information I need, because I also know acceleration due to gravity. So this time I can't use that cute little shortcut that we used in the example problem, because this time the rock was not launched horizontally. It was launched upward with an angle. And so I have to calculate the initial velocity both in the x and the y components. So the initial velocity in the x component is going to be 8.5 meters per second times the cosine of 30 degrees. Okay? And when I calculate that out, that's going to give me 7.4 meters per second. If I calculate the initial velocity in the y direction, it's going to be 8.5 meters per second times the sine of 30 degrees. And that's going to give me 4.3 meters per second. 2 significant figures, because that's what I had in my initial velocity. Okay, so I know my initial velocity. Again, if I'm going to calculate this distance, the horizontal distance is always dependent on time in the air. So that's the first thing I'm going to have to find, is how long was this thing in the air? I know the velocity in that direction, but the only way I'm going to be able to calculate how far it went is to know how long it was traveling. So I'm going to go to the y component of my direction so that I can calculate how long this rock was in the air before it hit the ground. Because again, once it hits the ground, it's not going to travel any further horizontally or vertically, either one. So the y component of my direction, if I'm going to calculate time, I know delta x, I know the initial velocity, I don't know time, but I do know acceleration. So I know everything in this equation except the time, and that's what I'm trying to find. So the delta x is a negative 100.0 meters. Why is it negative 100? Because this is where the rock started. Its final displacement was 100 meters below where it started. So that's why this is negative, and that's why it's 100. It did travel up, but remember, this is final displacement, and so the displacement was from here down to the cliff, or to the floor of the valley, okay? V sub 0 in the y direction was 4.3 meters per second, and I don't know time, plus 1/2 times negative 9.8 meters per second squared times t squared. Okay, now, granted, this kind of problem isn't a whole lot of fun because now I have to use the quadratic equation. Okay, that's not a fun thing to have to do, but in this case, there's really no other way around it, so you're going to have to use the quadratic equation. So the first thing you're going to need to do is to rearrange this so that you have it in ax squared plus bx plus c equals 0. So when I do that, I'm going to take this and I'm going to scoot it to the other side. This is my t squared component, so that is going to be negative 4.9, and I'm not going to put the units on there right now just so it doesn't clutter it up so much, so I can see what numbers are going to have to go in the quadratic formula. So I'm going to have negative 4.9 t squared plus 4.3 times t plus 100 equals 0. Okay, so then when I plug that into the quadratic equation, I'm going to have t equals, remember the quadratic equation is negative b, so there's negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay? Remember that when you solve the quadratic equation, you're going to get 2 answers. One of these answers will come up positive, the other one will come up negative. The negative answer for time is not logical because time doesn't have negative numbers, it doesn't go backwards. So only the positive answer is going to be the one that makes sense. And when I crunch all those numbers, the time ends up being 5.0 seconds. Okay? So now that I know the time, now finding out the x component of the displacement is easy because I'm just going to be able to use, again, delta x equals v sub 0t plus 1/2 at squared. There's no acceleration in the horizontal direction, so that piece drops out. So delta x equals the initial velocity in the x direction is 7.4 meters per second. And I figured out that the time was 5 seconds. And so my horizontal displacement comes up to be 37 meters. Okay? So again, it's the same principles as we used to work the problems where there was a horizontal launch. The only difference in this problem is that I actually had a number for the y component that wasn't 0, and so I had 2 numbers here. But once I got to that point, the way that I used it didn't change because I went to the y component to find time, and then I went to the x component to find the other piece of information that I needed, which in this case was horizontal distance. Yes, I had to use the quadratic formula, but that's algebra. That's not anything to do with making the physics problem any different. The same components are still there, okay? So you're going to have a couple of days now where you're going to be be able to practice these types of problems. And so just continue to work through them, be patient, say, okay, what do I know? Don't forget that you know acceleration in the y direction, you don't have it in the x direction. And just make sure that you keep all those components straight so that you can work those problems.